Hello everyone. Welcome to the video presentation on mechanical design of distillation towers by Group 16. In this presentation, we will cover the schematic design of distillation column, the types of common trays used, the effect of various flow conditions on tray design, parameters for column design. We will also discuss a stepwise procedure for design of columns. In our analysis, we have assumed that we have completed the chemical aspects of the design. That is, we have used the McCabe-Thiele method or the Ponchon-Chevret method to fix the number of stages of a column, the various flow rates, the reflux ratios, the reboiler ratios, and all other such parameters are predetermined. And we will only focus on the mechanical aspect of the design. Let us begin with the schematic design of a distillation column. Uh, In a distillation column, we have basically a shell and these trays that are arranged in a vertical stack-like manner. Mm. Uh, in each tray, we can see that there is some gap here, and there is an raised obstruction at the end of each tray. So this gap that we see here is the same vertical cross section of the tray. So this gap we see here is the downcomer. So this is the opening that allows the liquid to move from one tray to the tray below it. So it and the obstruction that we see is called the weir. So this weir acts like a dam, which allows the liquid to collect on the top of a tray. So when the liquid collects and the gas flows from the bottom, the gas and liquid form a dispersion at which the mass transfer can take place. And when the liquids moves down from one tray to another, the gas and liquid disengage. So that is the gas continues to move towards the top, and the liquid flows down into the next tray. So in a distillation column, we inlet the liquid from the top, and it flows down through the trays, whereas the gas is inletted from the bottom, and it bubbles through the liquid. And here, in each tray, that is the site of there is a vapor liquid equilibrium that is established at each tray, at which the mass transfer takes place. The vigorous bubbling of the gas makes the conditions very turbulent in this on the top of a tray, which increases the mass transfer coefficient, and hence the favors the transfer mass transfer between the gas and the liquid. There is a demister attached to the top, and the purpose of this is to prevent any liquid that might have been prevent any liquid from going up that might have been carried with the uh, gas flowing at a very high velocity. So we see that so the column mainly consists of a shell, and the column internals that we need to that will mainly focus are the trays, the weir, and the downcomer. Let us discuss more about the shell of a column. The shell of a column is generally made up of carbon steel or stainless steel. Apart from these materials, we can use other metals or alloys as well, but that depends on the corrosiveness of the fluids that will be moving inside the column. The temperature and pressure conditions at which the column will be operating also play an important role in this choice. The cost of the material is also an important factor. The diameter of a shell varies from 2 to 3 meters generally. Uh, the thickness of the shell can be calculated by using the standards reported in the literature. Few examples are the ASME Section 8 and IS 2825. The ASME is the American Society of Mechanical Engineers that has provided an international code that provides guidelines for the design of general equipments and mainly pressure based vessels. IS is the Indian standards for such equipments. So we can follow these guidelines, but we will have to ensure that these are only guidelines, and we'll have to take our own judgment into account as well while deciding while fixing these parameters. For example, yeah, if we consider a very high tower in which the number of trays is too high, then the temperature pressure conditions will be very drastic near the base, and will not be that much critical at the top. So we will have to use a column that is thicker at the base and thinner in the. We'll have to use a shell that is thicker at the base and comparatively less thick in the top. Using such a design helps us to save some cost as well. So so we need to take this account and take this into account and make some revisions to the guidelines as per our requirement, and that varies from the problem to problem. Moving on to the tray, we see the various parameters. We see that the residence time for mass transfer in a tray is roughly around 3 to 5 seconds. This means that when a liquid, when a fluid, when the liquid enters from the top, it must stay in a tray for around 3 to 5 seconds. We'll have to adjust the flow rates and size of the trays in such a manner. The length of the weir that we see is around 60 to 80% of the tray diameter. The area of the downcomer is 5 to 15% of the tray area. The height of the weir, that is the obstruction to the in which the liquid gas dispersion collects, is generally 1 to 2 inches. And there are these calming zones. In this figure, we see that there is some blank area between the weir and the sieves, that are the holes. So this blank area does not constitute into the active tray area, but it has some other function as well. So some other function. So these are called as calming zones. They can be labeled as inlet calming zones and outlet calming zones, and depending whether the depending on which side the liquid enters the tray. So the weir from which the liquid enters will be the inlet calming zone, and the other will be the outlet calming zone.
Okay, let's move to the next topic, which is types of common trays. So we will first see what are the various definitions of tray areas. So the first one is total tower cross section area. So this is mainly the area of the total tower without trays. Okay. Moving next, we have net area. So this is also called free area. So what is net area? This symbolizes that how much area, like the smallest area available for vapor flow in the inter tray spacing. Okay, so another one is bubbling area, which is also called as active area. So what is bubbling area? It represents the area we have for vapor flow just above the tray floor. The last one is whole area. So by name itself, it suggests that the area of the all whole perforations used on the tray. So that is basically the whole area. So moving next, we have different plate types there. So there are mainly three types of plates. One is bubble cap plate, another is sieve plate, and then whirl plate. So we will see all one by one. So the first one is bubble cap plate. Okay, so they consist of a riser here, and the riser is also called a chimney. So it will signify that why it is called a chimney. So the riser is attached to the tray with the help of a hole, and then a cap everywhere is mounted. So the a cap is here, which is mounted above it. So how does the flow happens here? The vapor flows through the riser and then moves to the annular region between cap and riser, and then disperses into the liquid which is flowing above it. All right, so this is the mechanism which follow uh, which is followed by the bubble cap plate. Also to note one main point, that the bubble cap plate is mainly used where there is higher turn down ratio is required. So what is turn down ratio? Turn down ratio is the ratio of maximum operating vapor rate to the minimum allowable vapor rate below which vaping starts. Okay, so this was also another point is that it is mainly used where there is very low flow liquid flow rate is there. Okay, we'll see the next one. So we have sieve tray. So it is also known as perforated plate. So by the name itself, we can tell that there are multiple perforations here, or these are also called as pitch holes. Yeah. So the common diameter of these holes are mainly from 1/8 to half inch in diameter. Also, the layout of these holes are either square shaped or maybe in equilateral triangular shape. How does the gas flow here? So the gas flow above from the perforations and then above to the liquid, it gets dispersed. Also to note, we can see that there is no liquid seal here, so the liquid can directly flow, and then weeping can happen. So that cannot be avoided here. So that happens here. And the sieve tray is mainly used where there is lower turn down ratio is required. And then we will move to the next last one, which is valve trays. So these are also known as floating cap plate. So this is basically the modified design of the sieve tray. So the holes are relatively larger, and there is a cap mounted here over the holes, and the shape of the cap can be round or maybe means circular. So it will be it might be round or rectangular in shape, and the same kind of mechanism follows here. The vapor flows into this, and then liquid it gets dispersed into the liquid. But what happens that weeping, which was happening in the sieve tray, it gets avoided here. So it just cannot directly fall into here. So that's valve trays. And it is also used when there is high turnover ratio is required. Okay, so we'll now compare one by one all the tray types. So if we talk about capacity, efficiency, pressure drop, and entrainment, the valve trays and sieve trays are almost similar. And if we compare the bubble cap with these two, so this bubble cap has lesser capacity, lesser efficiency, higher pressure drop, and then lesser entrainment as well. So in terms of turn down ratio, if we take the order, so there is bubble cap would be the would give the excellent turn down ratio, and then valve, and then sieve. Also in terms of cost, the sieve is the cheapest of all types, and the bubble cap is the costliest of all. So this is, we have summarized the all tray types in terms of different factors here.
So we are going to discuss about effect of vapor flow conditions. One of the effect is flooding. Flooding is condition is that due to excessive liquid buildup uh, inside the column leads to a column flooding condition. So this nature of flooding depends on the operating pressure of column and liquid to vapor flow ratio. It may be a downcomer backup, spray entrainment, or froth entrainment type floodings. The column flooding condition sets the upper limit of vapor velocity uh, for steady operation. Gas velocity through that area at flooding condition can be estimated using Faire's correlation. This is the formula for Faire's correlation, and uh, CSBF is a capacity parameter which is defined in the terms of flow parameters, FLG, and plate spacing. Uh, the operating vapor phase velocity is around 80 to 85% of UNF. Now the uh, second type of uh, condition we find that is liquid entrainment. So entrainment is the phenomena in which liquid droplets are carried away by vapor gas to the tray above. So the less volatile liquid components from bottom trays are mixed with liquid having relatively more volatile components on the overhead tray. It counteracts the desired mass transfer operation and plate efficiency decreases. So this entrainment increases with vapor velocity. So the fractional entrainment, that is kg uh, kg of that the amount of liquid uh, that has been carried away divided by gross liquid flow, can be also predicted using Fair correlation in terms of flow parameter and actual flooding velocity. So this is an example of flooding and entrainment in a distillation tray. As you can see, due to excessive vapor pressure, uh, due to as you can see in there, that due to excessive flow, the liquid is not able to come down, And when this flow increases very much, you can see how entrainment occurs. And let me go to the next slide. Uh, Now the next example is weeping. So weeping occurs at, in contrast to flooding and entrainment, weeping occurs at low vapor gas flow rates. The upward vapor flow through the plate perforation prevents the liquid from leaking through the tray perforation. So at low vapor plates, these liquids starts to leak through the perforation called weeping. And when none of the liquid reaches the downcomer at extreme weeping conditions, at very low vapor flow rate, it is called dumping. The weeping tendency increases with increasing fractional hole area and liquid flow rates. The vapor velocity at the weep point is the minimum value for a stable operation. So here we find out the minimum vapor velocity that is needed for stable conditions. Uh, so here is a video demonstrating the process of weeping. So as you can see that at very low vapor condition, these uh, water this our at very low vapor conditions, the liquid start weeping. Liquid from the the liquid from the, let me show you, liquid from these perforations of upper tray starts weeping.
Hello everyone, myself Rahul and I will talk about parameters for column design. It is very important for us to understand parameters used for column designing. And once the process design stage ends, the equipment design begins. And at this stage of design, we convert process requirements into actual hardware. Some important parameters are following: hole diameter. Commonly used plate diameters are between 3 to 12 mm, and as we increase the diameter of hole, chances of weeping increases. Holes are either drilled or punched, and the plate is constructed using stainless steel or from alloys other than carbon steel. Other important parameter is hole pitch. Hole pitch is defined as distance between centers of two adjacent holes, and normal range of hole pitch which we use is between 2.5 to 5 times of hole diameter. Next important parameter is plate thickness. Plate thickness typically varies 0.2 to 1.2 times of hole diameter, and plate thickness should be verified by checking allowed pressure drop. Next important parameter is column diameter. We can calculate column diameter by using Hairs correlation. Hairs correlation has been standard of industry for entrainment flood prediction. Hairs correlation tends to be conservative, especially at high pressure and liquid rate. Hair correlation gives us relationship for calculating superficial gas velocity. And to calculate superficial gas velocity, we need to calculate capacity parameter CSBF. And for a given formula, we can see that capacity parameter is calculated by using plate spacing and flow parameter. And for a given flow parameter formula, L and V represents liquid and vapor flow rates, rho V and rho L represents vapor and liquid density respectively. So after calculating CSBF by using this formula, we can calculate superficial gas velocity. And as we have calculated superficial gas velocity, it is very easy for us to calculate linear design gas velocity, which is approximately 80% of superficial gas velocity.
Column sizing is a trial and error calculation procedure starting with a tentative tray layout. The calculation is then revised until an acceptable design is obtained, subjected to satisfying the tray pressure drop, VPM flooding, and liquid entrainment limits. The column size is carried at the tray where the anticipated column loading is the highest and lowest for each section. However, the vapor flow rates have the highest impact on tower diameter. For example, the sizing calculation is performed on the top tray for the above feed section and on the bottom tray for each feed section for a single feed and column height. Lower tray spacing is desirable to minimize construction cost by checking against the column performance criteria. So now we will see the stepwise column design. So the first step involves determining the number of theoretical plates which we will be doing by the help of McCabe-Thiele method. And second will involve now the second step will involve the physical properties of the system. Physical properties of the system involve column top pressure, column pressure drop, surface tension for components in the top section, and also for the bottom section we need to get the CP values using the steam table. Now third is selecting a trial plate spacing. We first of all guess the value of plate spacing to calculate the capacity parameter for estimating the maximum allowable vapor velocity through net plate area. Now the next step involves the estimating the column diameter based on flooding considerations. The flooding considerations, excessive liquid built up inside the column leads to the column flooding conditions. Nature of flooding depends on the column operating pressure and liquid to vapor flow rate. Column diameter is determined from the flooding correlation for a chosen plate spacing. Uniformity in tower diameter may require selecting different plate spacing in different sections of the tower. Next is deciding the liquid flow rate, reversible, single or multiple pass. We will determine which liquid flow rate gives us the maximum efficiency. Okay. Now next is making a provisional tray layout, like including down comma area, active area, perforated area, etc. Like plate hole diameter. When we calculate the plate hole diameter, it usually ranges from 3 to 12 mm commonly. Now center to center distance between two adjacent holes is what called as the hole pitch. Now, what is a wire? Depth of liquid on tray is maintained by installing a vertical flat plate, which is known as the wire. Higher wire height gives more efficiency. Wire length determines the down comma area. Is the wire length will determine as the down comma area. Now the seventh step is involving the weeping rate. The seventh step involves the weeping rate, which is not satisfactory. Then we need to go back to the step 6 and select the tray layout. And weeping flow rate is already described above. Now the checking the plate pressure drop. Okay, we need to now check the total pressure drop, the dry plate pressure drop, residual gas pressure head, down comma backup, and down comma residence time. Dry pressure drop occurs due to the friction within the dry short holes, whereas residue gas pressure drops results mainly from surface tension as the gas releases from a perforation, because the friction will generate and this will give us the residual gas pressure drop. Okay, residence gas pressure drop. Okay, then now the next thing is down comma backup. Now we have to get the down comma backup. Down comma backup, it occurs when the hydraulic head requirement to flow liquid through the down comma exceed the height of the down comma itself. This lead to increase in the liquid flow rate, while tray pressure drop also increases when vapor rate is raised. When the backup liquid in down comma exceeds the tray spacing, liquid accumulates on tray above. So if too high down comma is there, we need to go back to the step number 6. Now the next step is determining the calming zones and perforated areas and checking the whole pitch, and if it is unsatisfactory, go back to the step 6. So what is the calming zones? It is the blank area which are provided between the inlet downcomer or inlet wire and the perforation area, and also between the outer wire and perforation area. The inlet calming zone helps in reducing excessive weeping in this area because of high vertical velocity of entering liquid in downward section. Outer calming zone allows disengagement of vapor before the liquid enters the down comma area. Uh, Calming zone usually occurs calming zone is usually suggested of 50 to 100 mm. 50 to 100 mm is usually suggested. Now the next step is to recalculate the flooding based upon the selected tower diameter. Now 12th step is in like checking for the entrainment, and entrainment we have already defined above. Now third and 14th are the last steps, which is just to finalize the readings which we have gotten. After seeing the readings and making the logistics out of it, we will make sure that we are having a best efficiency and best utilizable, which is involving both the capital cost and good for the industry. If it is not satisfying the capital cost, it is overshooting it, we need to describe we need to go through the process again till the time we have the output best output and efficiency ratio. Thank you. That's the end of the project.